Hello, and welcome to Math with Mr. Bill. I'm Bill Anderson. We're going to look at a problem that is going to ask us to evaluate an integral using the limit of a sum. One of the ways to define an integral, one of the ways to define the Riemann integral. So, first thing we want to do is write up what the limit of this sum that we're going to be finding. So, in general, for a Riemann sum, the integral between a and b of some function is equal to the limit as n goes off to infinity of the summation from I equals 1 to n of f of x sub I times delta x. Sometimes you'll see it as delta x sub I. And that's what we're going to be concentrating on for this problem. So when we do this, we have a couple of things we need to find. We need to figure out what x sub I is, and we need to figure out what delta x is. So delta x is going to be equal to our right endpoint minus our left endpoint divided by n. And our x sub I is going to be equal to, it kind of depends, but generally it's equal to 1 plus I delta x. I'm sorry, not 1, but that's specific for our problem, but in general it's equal to a plus I delta x. So, and there's a little bit of problems if the indices are, if you start at 0 instead of 1, you have to adjust things around. But for what we're going to be doing, this is going to be your formula. So let's find the things for our function. So we've got the integral now from 1 to 2 of x cubed minus x squared dx. And that's going to be equal to the limit as n goes off to infinity of the summation from I equals 1 to n of f of x sub I, which is going to be x sub I cubed minus x sub I squared. And then all of that is going to be multiplied by delta x. So let's find our delta x and our x sub I and plug them in and start to turn the crank on this. So delta x is equal to b minus a, so 2 minus 1 over n. So that's just equal to 1 over n. And then x sub I is going to be equal to 1 plus I delta x, so I times 1 over n. And I'll leave it like that. So now our limit of our sum, limit as n goes off to infinity, of the summation where I equals 1 to n of x sub I cubed. So instead of x sub I, I'm going to put 1 plus I over n cubed minus x sub I squared, which is 1 plus I over n squared. And then all of that times our delta x, which is 1 over n. So now we've got some expansion to do, and we should probably, let's get both of these expanded, then we'll combine like terms, and then we'll talk about how to evaluate it from there. So we get equal to the limit as n goes off to infinity. So the expectation here is that if you don't have the expansion memorized, that you go off and you figure out what the expansion is. It's not impossible. It's just tedious. Here we'll just go ahead and write it out. So it's the first term, 1 cubed, plus 3 times 1 squared times the second term, plus 3 times 1 times the second term squared, so I squared over n squared, plus 1 times the second term cubed, so I cubed over n cubed. And then minus, I'll keep this in parentheses right now, 1 squared plus 2 times 1 times I over n, so 2 times I over n, and then plus the last term squared, so I squared over n squared. And all of that is times 1 over n. Okay, let's go ahead and combine like terms here. So the 1 minus 1 go away. And then we have 3i over n plus minus 2i over n. So that's going to give us 1i over n. And then we have 3i squared over n squared minus I squared over n squared. So that's going to give us plus 2i squared over n squared. And then plus I cubed over n cubed. And so all of that is going to be multiplied by 1 over n. And we'll fill in the summation and the limit really quickly. Okay. So now the last thing to do is to go ahead and multiply the n in. So we have the summation and the limit. Basically copy and paste that. And so then you get I over n squared plus 2i squared over n cubed plus I cubed over n to the fourth. Now generally here now we separate this into 3 different sums, and since the summation is only acting on I and the limit's acting on n, we pull out the 1 over n to whatever exponent out in front of each of those. And we can pull out constants too. So in this latest step here, we're going to get, now for the first summation, we're going to get 1 over n squared times the summation of I plus 2 over n cubed times the summation from I equals 1 to n of I squared. And then lastly, 1 over n to the fourth times the summation from I equals 1 to n of I cubed. Now each one of these summations has a formula. And usually they're written down in your book somewhere. And it's going to be something you have to memorize, or if you get a note card, put it on your note card. Like the summation of 1 is n times, summation of I is n times n plus 1 over 2. The summation for I cubed is n times 2n plus 1 times n plus 1 all over 6. And then the last one is n squared over n plus 1 squared all over 4. So now, since we've replaced all of our sums with these closed formulas, then when we expand, multiply out each of these binomials and multiply each of these factors out, we're going to get polynomials in the numerator that are going to have the same degree as the n in the denominator. So, and that'll be useful for finding the limit and then being able to figure out the total integration. So for this first one, we get 1 over n squared times, and distribute the n, get n squared plus n all over 2, plus 2 over n cubed. And so this is 2n times n, which is 2n squared, times n, which is 2n cubed. And then 2n times 1 is 2n plus n, that's 3n, times n, which is 3n squared. And then plus 1 times n, which is just n, all over 6. And then we get n plus 1 squared all times n squared. So for the sake of time, we'll just go ahead and get that all written out. So that's n to the fourth plus 2n cubed plus n squared. And I encourage you, if that's too fast, just stop and do it. Take n plus 1 and square it. And then multiply the resulting trinomial by n squared and make sure that I'm getting the right answer. So now we can kind of clean this up a little bit if we need to, and we can also start to take a look at what we have in terms of our limits. So the 2 and the 6 here, those will reduce a little bit. And then we have, We've got a whole bunch of fractions, and we can break those up even into more fractions if we want to. And that might be useful for this version of this problem. So we have n squared over 2n squared. And then plus n over 2n squared. And then plus 2n cubed over 3n cubed. And then 3n squared over 3n cubed. Plus n over 3n cubed. Plus n to the fourth over 4n to the fourth. Plus 2n cubed over 4n to the fourth. And lastly, n squared over 4n to the fourth. So taking the limit of any of these fractions where the degree on the top is less than the degree on the bottom, they're all going to become 0. So we can cross out all of those and mark them as going to 0 in the limit. What remains now, all of these fractions that are left, the power on the top and the power on the bottom, those are all going to cancel. And so we're left with 1/2 plus 2/3 plus 1/4. And if we get a common denominator, each of those go into 12. So we get 6/12 plus 8/12 plus 3/12. And we add those together and we get 17/12. And there's the sum. That's going to be our integral from 1 to 2. And hopefully work some of that algebra out and get that, or some of that arithmetic out too, and get that all taken care of. So anyways, if you have any questions, feel free to put them in the comments below. If you have any other problems that you'd like to see done, please put them down there as well. Otherwise, thanks for watching. Appreciate you watching, and I will see you on the next problem.